So, when a giant molecular cloud collapses under its own gravity, all the mass rains down in the middle. Some little fraction of it might have almost no angular momentum and end up forming a lump in the middle, which might turn into a star, but the vast bulk of the matter has too much angular momentum, and so will end up as a spinning disk around it. So the next question is how you turn such a disk with a little lump in the middle into our own solar system, or something like our own solar system. The trouble is, the lump in the middle is only made of the stuff that comes down that had no angular momentum, and there isn't very much of that, so this will be much smaller than the mass of our current sun. So in this situation, most of the mass is in the disk, only a little in the middle. But in our own solar system, as you recall, nearly all the mass is in the sun, in the middle. So somehow we need to get some of the mass that's out here in the spinning disk, what's called an accretion disk, into the center. And that's a bit tricky because all the stuff around here is orbiting perfectly happy. It has just enough speed to balance gravity. Centrifugal force balances gravity. There's no reason for it to fall in. It's all spinning quite happily out there. Now this is a very common problem. So the study of accretion disks, these disks around masses, is a very important branch of astrophysics. It's important for protoplanetary disks, but it's also important for quasars. If you remember, they also had a disk around them with matter falling in. So here's the basic idea. Look at the, say, this bit of the disk. Let's pick an annulus, a ring around here. Now it's going to be moving with some velocity, equals root g m over r. And now let's consider the next ring further out. It's a little bit further out, so this one is going to be, let's call that r1, and this one's going to be gm over r2. So here's r1, and there's r2. What this means is the velocity in this dark blue ring is going to be a little bit smaller than the velocity in the bright blue one. So you've got two rings, donuts of gas, travelling at different speeds, but they're right next to each other. So what that means is they're going to be rubbing. So you get, if you look up close, this one travelling quite fast, and this thing going a bit slower. There's going to be rubbing between the two, viscosity. Viscosity is fluid friction. What this means is the fast-going stuff is going to be slowed down by the friction with the slow-moving stuff further outside. As it's going to be slowed down, its velocity will drop below this level. As velocity is dropping below that level, centrifugal force is no longer strong enough to overcome gravity, so the gas will actually start moving in. Likewise, the stuff further out, it's got friction, friction from something moving fast near it, and that's going to try and drag it along and make it go faster, so its velocity will go larger. Now the centrifugal force will overcome friction, so it will start moving out. So if you get viscosity in a disk like this, and let's say the disk started off at these sort of radii, what's going to happen with time is that some of the matter is going to start coming in. The inner part of the disk will move closer and closer to the center, and some mass will eventually end up falling into the star. And also, some will go further out. So the disk will expand, but some matter will fall into the center. And this is just what you need. It turns out that if you do the calculations and you assume some simple viscosity, most of the mass will end up falling into the center, but a small amount of mass will go out to a huge distance where it contains lots of angular momentum. And that's exactly the situation in our own solar system. In our own solar system, mass is in the middle, in the sun, but the angular momentum is actually mostly in the planets. Remember, angular momentum is mvr. The planets have a very small mass compared to the Sun, but they're much further out and they've got higher velocities. So in fact, this term overpowers that term and most of the angular momentum is in the planets. So this sounds pretty good. We move the accretion disk moves most of the mass in, but some small fraction of the material goes further out, and that small fraction of gas and dust and things further out might turn into planets. Unfortunately, there is a problem. To make the whole thing work, we need some sort of rubbing. We need to exchange angular momentum between adjacent parts of the disk. So if you've got a fast-moving bit here and a slow-moving bit there, the fast-moving bit needs to cause the slow-moving bit to speed up, and the slow-moving bit needs to slow down the fast-moving bit. Now, the normal way we do this is viscosity, fluid friction. The only trouble is, fluid friction as we know it is tens of thousands of times too weak to make this happen. Basically, these gases are pretty tenuous, and this change in speed over short distances is pretty small, so in fact this viscosity would act far too slowly. It would take billions of years to actually get the mass moving in the middle to form a star. And we haven't got billions of years. We know that solar systems can actually form on timescales of only millions of years. So what we need is some stronger form of friction, some way to couple the inner fast-moving and the outer slow-moving bits of gas, link them together somehow so that the fast-moving bits can pull on the slow-moving bits and vice versa to make the matter go in and the angular momentum go out. Now, when I first taught courses about this 10 or 15 years ago, we had no idea what's doing it. We now do have an idea. What's causing these things to be coupled is what's called magneto-rotational instability, or MRI. The basic idea is we have our spinning disk, and there are magnetic field lines. Magnetic fields. The magnetic field lines go from the inner bits to the outer bits and act like elastic bands, tying them together. And so as the inner bits spin around really quickly, the magnetic field lines get stretched out and pull on the further out bits. Now, for this to work, we need magnetic fields to link to matter. If the matter is moving, it's got to drag the magnetic fields with it. If the matter is going slowly, it's got to hold the magnetic fields back. And this doesn't normally work. In my room as I sit here, there is a magnetic field, the Earth's magnetic field, but it doesn't stop me moving around. I move around, but the magnetic field lines stay exactly where they are. So that's not going to work. Surely the matter can just orbit however it likes, and the magnetic field lines, which link things together, have no effect. Well, not quite. If you have electrically neutral matter, like me sitting here in my room, then sure enough the magnetic field has no effect. I can walk through a magnetic field and leave it alone. But let's say you have a plasma. So ionized matter, so you might have electrons and nuclei split off. In this case they've got negative and positive charges. Now consider something with a negative charge that's moving. There's a word for that. It's called a current. Moving charge is a current. So what we have here is a current, and let's say we have a magnetic field, so magnetic field lines going past. As you may remember, if you have a wire with a current flowing down it, and you have a magnetic field, the wire will experience a sideways force. Lorentz law. So what this means is the same thing applies here. You have an electron that's moving through a magnetic field, and it's going to experience a sideways force. What that will do is it will bend its motion. It will cause it to curve. As it curves round, it will still experience a sideways force because now the current's going this way. So in fact what happens is, if you have a magnetic field and moving charges, the charged particles will actually go in rings, or more commonly spirals, around the magnetic field lines. So what this means is, if this disk of gas is ionized, that is to say some fraction of the electrons have been knocked out of the atoms, and there's a magnetic field going through it, and there's magnetic fields almost everywhere in space, then the atoms, the charged particles, can't go wherever they like. They just have to go in spirals around the magnetic field lines. And the same thing applies in reverse. If the electrons are all being pushed some way, they carry the magnetic field lines with them because they're all going in spirals together. The two are bound together. So this is believed to be what causes matter to fall in, to make the sun so big, and moves the small amounts of material further out, so you get so much angular momentum in the planets. So magnetic field lines get tangled up from the inside to the outside, and because the gas is ionized, the matter and the magnetic fields are coupled together. They're locked together. They can't move without each other. So that solves one problem, but it introduces another problem. Why is the gas ionized? In a disk around a quasar, it's so hot it's no wonder these things are ionized, but disks around protoplanetary disks around new forming stars, are not so very hot. Right in the middle, you've got the light from the forming star, and so the inner part of the disk might be hot enough to be ionized. Further out, you might get ultraviolet light from nearby new forming stars, which might produce a bit of ionization, but many models predict there's a dead zone in the middle. Too dense to be affected from ultraviolet from outside, too cold to be affected by the sun, and in this region, the positive and negative charges are bound together, called atoms. And because they're bound together, they have no net charge, and they can completely ignore magnetic field lines. So this whole idea of magnetorotational instability says that the accretion disks funnel matter to the middle because magnetic field lines link different parts together, but it has problems with dead zones, and that's a real unsolved mystery at the moment.